And so it begins. In quantitative analysis, I opened up the lectures with a statement about how we interact with the world through our senses. So the point of instrumental analysis is similar in the sense that by creating instruments and taking advantage of electronic components, we're enhancing our sensory information or our ability to sense things. So there are three types of phenomenon. One is the electrification, which is the generation of an electrical potential based on some physical event. There's resistance, namely the response of the material to the electrification, and in this case it's strictly linear. And then there's capacitance and inductance, which is a slightly different response to electrification event, and this is nonlinear. So just to reinforce this and for the standpoint of the mathematics, resistance is linear, capacitance and inductance is nonlinear, and we're going to see that the equations that describe these events differ as a result. So in the case of resistance, it'll just be a simple linear equation. In the case of capacitance, you're going to wind up with differentials and integrals. A concept from systems analysis, in other words, looking at a complete functional entity, which would include you as the observer, the instrument, and the sample. So again, think of the human body, the intelligence within the brain, the interface, how the brain or the mind interprets the world around us. It goes through our senses. Instruments the same way. So there's an observer controlling intelligence. Controlling intelligence could also be the software that operates, or actually there are mechanical computers as well, but the workings of the machine that take the sample and then measure the response. The sensor is the information gathering device, and the actuator is the device that will act according to the information received. So as an example, take my little friend here, the controller. The controller here has three fundamental questions, namely, is it? Like as in, is it a case, is it tuna? How many? How many cans did you buy me? How much? How much tuna? What's the weight of the tuna in each of the cans? So if you look at those three types of questions, they differ in the logic statement. So think of a switch as the practical device, open, closed. So it's binary, like digital logic. How many? We have devices called counters, and you're talking about cardinal value numeric numbers, counting numbers. How much? Analog sensors, you're looking at real variables where you can have any number of possibilities. So the real number system, in other words. And again, recalling our relationship to the senses, this is how the information can get to us. We call them channels. So the visual, mechanical, hydraulic, pneumatic, and these are all actuators, electrical stimulus, and messages, coded information. So our first device, so to speak, is a voltage source. So by definition, it's a generator of electromotive force. Some disequilibrium in the system causes charged particles to move through a circuit if the circuit is available. If it's not available, then there is a potential. I'm going to symbolize these things eventually, but think of it as the battery and mechanical turbine. So these are two common ways to make this work. The potential energy is analogous to that of mechanics. So if you hold a book above the floor, there is potential. And if you release that book, it translates to kinetic energy. Similarly, if you have a battery, the chemical reactions that are, or the chemical potential of the reactions that can occur inside a battery lead to potentials at the poles of the device. If those poles are connected via a circuit, then the electrons will flow. The symbol I'm going to use is this unequal parallel bars. I'll indicate polarity with a plus sign, and the high plus sign indicates the high potential. So the current is going to flow from the position of high potential to that of low. I'm going to make a subtle distinction between two types of devices. So a transducer is one that converts energy from one form into another. A sensor is something that provides an energy signal corresponding to a particular situation. So as examples, we've got a photovoltaic cell that when light strikes the cell becomes a voltage source. It generates a potential inside the device which would be detected as what we call a voltage. A sensor, on the other hand, would take advantage of the behavior of a resistor. If you heat a resistor, the resistance value changes, so that if you have a circuit as illustrated in the diagram here, a voltage source that's static, not changing, pushing current through the circuit that consists of two resistors and a current meter. We'll discuss how the current meter works in a later part. But if the heat alters the resistance value of that resistor indicated, it would necessarily change the current according to Ohm's law flowing through the circuit. So that would be a measurable change dependent upon the resistance value of the resistor. My little friend has many questions, this time about the sensors of the transducers. So these are the types of questions you ask when you create or devise a new circuit or a new device to make the measurements. So namely, does the sensor have an effect on the system? What's the response time, repeatability, linearity? Linearity is nice because it allows you to create calibration curves based on simple linear forms. Backlash refers to if the sensor makes a measurement in an increasing fashion, if it goes back, in other words, when the stimulus stops, does the value of the sensor change? Does it sort of drift after it's been primed, so to speak? Sensitivity, what's the minimum signal that you can detect? Do other variables in the system that aren't important, do they affect the sensitivity? What's the maximum error? And what is the accuracy of the service? And ultimately, does the thing degrade? So the voltage source, as we've seen, is a device that generates an electrochemical or electromotive force, which we call voltage. The terms are synonymous. You don't so often in the current literature see reference to electromotive force, but it is a more descriptive, at least tells you what's going on in the device as opposed to just saying this thing has a voltage. So we saw the photovoltaic device where an external source of energy is converted into an electrochemical potential. The same occurs in the case of, say, a battery. You have these agents, these chemicals inside a package, and if they are allowed to react in a controlled fashion, they generate an electrochemical potential. So the chemical potential energy of the molecules is converted into an electrical or electromotive potential energy. There are notes in quant you can refer to regarding this. So the voltage actually represents a spatial difference in the electrical potential of the system. So the charging phenomenon are varied. They can be mechanical, thermal, chemical, electrical, or magnetic fields. So the field effects, radiant energy, and atomic energy. So these are all phenomena. They're energetics of some sort, and they can be converted into an electrical potential. If you've heard of Nikola Tesla, his big thing was the transformation of electric and magnetic fields and motion. So some representative types of charging phenomena, recognizing again that what you're doing is having some form of energy redistribute the charge in a device, separation of positive and negative charges, and this translates or is definitive of voltage. So you can electrify things by mechanical energy, gravitation. This is how lightning forms. Inertia, and this is really kind of cool when you think about it. If you spin a metal disc where you have the conduction electrons that are free to move, and you halt the disc, the electrons, because of inertia, keep moving inside the metal, and they generate a charge within the metal body. It doesn't last long. I mean, but it's like halting the brakes on a cartoon character, and the coyote goes off the cliff. Contact electrification. So this is frictional. If you've ever pet your cat and created sparks, that's the sort of thing. Piezoelectric is quite interesting. If you compress or elongate a crystalline structure, you can disrupt the charge inside the crystal, namely the valence electrons, and you can create a charge that way. If you try thermal energy, there are various phenomena. So there's pyroelectricity, thermoelasticity, thermoelectric. They're all quite related. What you're doing is essentially replicating that mechanical stress, that piezo I mentioned in the previous highlight, doing it by thermal means. So you're causing movements of the charged particles within the material according to a thermal gradient. Chemical you're familiar with if you work with batteries, or if you've ever used a battery, you probably have. So you have a coupled oxidation reduction reaction. You package it so that they can't spontaneously occur. And then so each compartment in the battery has chemical potential energy waiting to be released. And the means of release is the completion of the circuit. So the connecting the two poles of the battery with a wire puts in contact those two chemical reaction systems. The communication between those systems is the electrons, but those are what will be communicated if you put them in contact. Recognizing that if two metals interact oxidatively, they transfer electrons directly. The only difference between a battery and doing this reaction in solution is that you're using a wire as an intermediary, and it is allowing the electrons to flow through the wire. Direct chemoelastic, again, is another means of doing this in a more controlled fashion. I'm sort of having a brain glitch here. It's a chemo. You're allowing the reactions to take place directly. You slow them down a little bit kinetically by putting in a barrier. So as opposed to having the wire there, you have, say, a membrane. And this is how fuel cell works. Electric fields, you can polarize materials. So this is, again, Tesla. If you keep cutting through fields, and you will, say, put a magnet in and out of a wire loop, for example, this is the Faraday effect, you can cause shifts, inductive shifts in the charges within the solid. So, and if you keep redoing this repeatedly, you will generate a regular current. Radiant energy, again, this is usually ionization phenomenon. So if you have a high energy photon, whether it's coming from radioactive decay, ultraviolet light, even visible light, if you're working with specific materials, you can cause excitation of the molecular or atomic state. And once excited, the electron that has put into the excited orbital is better able to flow and move through the system. So photosynthesis works this way in the visible light. So the molecules, the proteins and the pigments of the photosynthetic membrane have energy levels that are packed closely enough together that it takes light of relatively low energy, namely near infrared, to excite the electron, and then once the molecule is excited, the electron that's been promoted is free to be donated to an acceptor molecule, and there's a cascading effect through proteins and metalloprotein complexes. Atomic energy, same thing. Again, blast the electron into space. And finally, this concludes this part. These are a number of two books in particular that I used to create the lecture, and they're good reference materials.